Hello everyone, and welcome to Jam Academy. In this very important example, I want to show you how to use the work kinetic energy theorem to analyze a complex system. I've actually given this problem countless numbers of times in my final examination, so it's important that you pay attention. And if you do not understand any aspect of this problem, please do participate in the discussion forum below this video. It's important you get this right. In a physics research project, a box of mass m is given an initial velocity v0 at the bottom of an inclined plane at an angle theta to the horizontal. The inclined plane is rough, with a kinetic friction coefficient mu between the box and the inclined plane. You are required to use, remember I've specifically asked you to use the work kinetic energy theorem to calculate the maximum height attained by the box on the inclined plane. You can use Newton's laws of motion to do this problem. You can use the law of conservation of mechanical energy to do this problem. As a matter of fact, you will see this problem again in the future. And we are going to use the law of conservation of mechanical energy to analyze this problem. But now, I just want you to use the work kinetic energy theorem to solve this problem. Work is the transfer of energy when a force moves its point of application. As a matter of fact, whenever work is done, energy is transferred. Now, the work kinetic energy theorem is a fabulous theorem that tells us what happens to a system whenever work is done on or by the system. You see, the net work done on a system is just equal to the change in the kinetic energy of the system. That is as simple as it gets. So in order for you to apply the work kinetic energy theorem, there are two things required of you. Choose 2 points, the initial and the final point. The choice is yours. Now, when you choose 2 points, calculate the kinetic energy at the initial point, the kinetic energy at the final point, then equate the change to the net work done on the system. Then you will be able to solve the problem. Let me demonstrate that to you here. So I'm going to choose 2 points. This is point A and this is point B. So the kinetic energy at point A, remember the object at point B is at rest. So what does that mean? It means that the kinetic energy at B is 0. As a matter of fact, at maximum height, whether is it a projectile thrown up and caught again or an object sliding up an inclined plane, at maximum height, the velocity, the instantaneous velocity is always 0. Keep that in mind. So that being said, we therefore can see that the kinetic energy at B is equal to 0, but the kinetic energy at A will be equal to 1/2 mv0 squared. This essentially implies that the change in kinetic energy will be equal to 0 minus 1/2 mv0 squared. Hence, we can say that the change in the kinetic energy is just negative 1/2 mv0 squared. Let us put this in a bracket. So the next step, step 2, which is a big one, is to calculate the net work done on the object. To calculate the net work done on the object. This is the fun part. In order for you to calculate the work done on an object, you need to know the forces acting on that object. Let me say that again. To calculate the net work done on an object, you need to know the forces acting on that object. In order for you to know the forces acting on the object, I recommend you draw a free body diagram. But what is a free body diagram? A free body diagram is just a schematic diagram that shows only the forces acting on an object. It does not show the forces exerted by the object. So keep that in mind. So let's draw our free body diagram on this object. The weight of the object acts vertically downwards. Pardon me. It acts vertically downwards. So this is mg. The object, the box, is moving upwards, so the friction force on the box will act in the opposite direction to the box. We have here the normal force, F normal. So the next thing I would like for you to do is to recognize that, one, this angle is theta. And if that angle is theta, we can resolve the weight of the box into two components. You have here mg cosine theta. You have here mg sine theta. So these are the forces acting on the box. Remember that the total work on the box is equal to the work done by the normal force plus the work done by gravity plus the work done by kinetic friction. So we have to calculate the work done by the normal force. We have to calculate the work done by gravity, and we also have to calculate the work done by friction. The box is moving upwards. I'm going to choose my coordinate axis so that it lies along the plane. So now the work done by N is equal to Fn multiplied by the distance moved up the inclined plane multiplied by the cosine of the angle between Fn and the displacement, which is 90 degrees, and this is just going to be 0 because cosine of 90 is 0. Similarly, the work done by gravity, it's going to be equal to the force, the component of gravity in the direction of displacement multiplied by the displacement. So this is going to be mg sine theta multiplied by d, and we're going to put here cosine of 180 degrees. This is important. Most students might miss this. And that will, the cosine of 180 degrees is just -1. So this is just going to be equal to negative mg d, the sine of theta. Now, the work done by friction, is going to be equal to the friction force multiplied by d. So the question is, what is the friction force? By definition, the friction force is just equal to mu k Fn, which is equal to mu k mg cosine theta. This is going to be equal to mu k mg cosine theta. Hence, the work done by friction will be equal to negative mu k mg cosine theta bracket d. This is just equal to mu k mgd, the cosine of theta. Now that we have everything in place, so we can see that the total work done on the object will be equal to 0 minus mgd sine theta minus mu mgd cosine theta. We can factorize this out, but remember, we have been asked to calculate the maximum height. In other words, we have been asked to determine this distance, the maximum height, h max. So how do we calculate that distance? This distance from here to here is d. So how do we relate that distance? We know that the sine of theta is equal to h max divided by the hypotenuse, which implies that h max is equal to d sine theta. That's what we know. Another way of seeing this is the fact that d is equal to h max divided by the sine of theta. So all we have to do is replace this d and that d. So if we do that, we have the total work equal to negative mg d, which is h max divided by the sine of theta. This is sine theta minus mu mg d, which is h max divided by sine theta multiplied by cosine theta. Sine cancels off with sine. We have negative mgh max, negative mu mgh max, multiplied by cosine over sine is cotangent theta. Remember, cosine theta divided by sine theta is just cot theta. All of this is equal to 1/2 mv naught squared. And we've been asked to calculate v naught. So what do we do next? We can factorize out h max. So we will have here, this is negative h max. I'm going to factorize out negative m h max brackets. We are left here with g plus let's factorize out the common terms. Negative mg h max bracket 1 plus mu cotangent theta is equal to negative 1/2 mv naught squared. The negatives, this can take care of this, and we are left with h max equal to v naught squared divided by 2g bracket 1 plus mu cotangent theta. So this is the expression to calculate the maximum height risen by the object up a rough inclined plane using the work kinetic energy theorem. Now, this is a very beautiful theorem, And if you have not understood the problem, please do not hesitate to ask your questions in the discussion forum below. Thank you so much and have a wonderful day. Bye-bye.